All right. So now let's demonstrate an example of how we do this. Suppose we've got the function um, f of x equals x squared right here from 0 to 4. That's all we're interested in. And so we want to find the area. So we'll put a little line there to 4 to kind of give us, to help us see the shape, right? So we've got this shape here. So we want to find the area of this weird little wedge shape right here. Let's use the right hand rule. So the right end point rule, or I call it or the right end point approximation. That's what they call it. I always call it the right hand rule. Okay, so here's the process for doing this. The first thing we do is we figure out, okay, how many rectangles do we want to cover with this with? So let's start with n equals 4. Okay, so if we use n equals 4, then delta x is b minus a over 4, or in our case, 4 minus 0 over 4. So each rectangle will have a width of 1. Okay. Now with the right endpoint rule, remember, and we could draw this in. So basically, we've divided this interval from 0 to 4 into 4 sections, and we're using the right end of each of those subintervals to determine the height of the rectangle. And so there we go. So those are our rectangles. Now what's important is with the right end rule, you start with x sub 1 as your first x. Okay, with the left end rule, you start with x sub 0, and so you would use this one, this one, this one, and this one. Okay, but with the right end rule, you use x sub 1, 2, 3, and 4. All right, so we know what the formula is going to be, right? For the area, it's going to be the area. Like we demonstrated in the previous example, it's for each rectangle, so let's write this down. The area of the ith rectangle is simply the width of the rectangle, which is always delta x, times the height, which for the right end rule, it's going to be found by plugging, not, let me try that again, x sub I into the function. And that'll give you the height of the ith rectangle. If this was the left end rule, this would be, we'll put this down here, this would be x sub I minus 1, if that's for the left end rule. Okay, but that's the area of the the area of the ith rectangle, and we want to do that for all 4 rectangles, and then we want to add those up. If you go back into our previous notes, you'll see this, that the area of the right area of 4 rectangles is equal to delta x times the sum of, from I to n, f of x sub I, right? Now, let's just work out x sub I. Remember this. X sub I is equal to the x sub 0, which is a, plus I times delta x. All right, so again, look back in our, it's important that we have this little formula that gives us the value. So x sub I, and this is for the right, is a, or 0, that's a, right? 0 plus I times delta x, or in our case, it's just I times 1, right? Delta x is 1. So x sub I is simply going to be I in this case. Okay, I times delta x. Okay, this is just for n equals 4, by the way. All of this is for n equals 4. If we change n, then of course delta x changes as well. Okay, but in reality, it's just I. So basically, we're looking at the sum of the delta x's times the sum of I equals 1 to n of f of x sub I. Now I'm going to write it this way because I do think it's helpful. Delta x is 1, And then we're going to take times f of our first right endpoint, plus f evaluated at our second right endpoint, plus f evaluated at our third right endpoint, plus f evaluated at fourth right endpoint. And those are nice and easy in this case because we only we were going from 0 to 4, and we only divided it into 4 regions. So all I got to do is to find the sum of these areas is do 1 times f of 1. So remember our function is x squared, so it's going to be 1 plus f of 2, that's 2 squared, plus 3 squared, plus 4 squared, or 1 times 1 plus 4 plus 9 plus 16, and so I think that's going to be 30, right? And so that's the area under those 4 rectangles, right? So that would give me my first approximation, and then I would redo this process. Let's just do it one more time. I would say now if I want a better approximation, for a better approximation, use a bigger n. So let's use n equals 8. So it's going to look like this. Delta x will now be 4 minus 0 over 8, or 1/2. The formula for the different i's is going to be still a plus I times delta x, or just 1/2 I, gives us each of the different i's. And so the right end rule using 8 rectangles is going to be delta x times f at, I can just use this formula, plugging in a 1/2. That's my first right end point. Now plug in a 2, f of 1. Now plug in a 3, 3/2. And I'm going to not have room here. Plug in a 4, f of 2. Plug in a 5, f of 5/2. Plug in a 6, f of 3. Plug in a 7, f of 7/2. And plug in an 8, f of... So now if I evaluate all of those, the function at all of those 8 points, add those up, multiply by 1/2, that's going to give me that. So let me just take a moment to do that real quick off screen so that you see the number. And so after I do all that, and remember, multiply by 1/2, I get 25.5. Okay? So just for the record, all right, just for the record, the area here is the actual area here, which I know by other sources, is 21 1/3, right? So that's the area. That's the actual area. But you can see that we're getting closer. We started at 30. That was when we used 4 rectangles. Then when we bumped that up to 8 rectangles, we got 25.5. So you can see we're coming down, right? And so this is using the right end rule. Now, of course, if you use the left end rule, then the process continues the same, right? You're just using the left end sides, okay? And then we finally have what's called the midpoint rule, which uses the middle point, all right? And so the tricky there let me squeeze this in here. For the midpoint rule, right, the only thing that changes is your formula for the x sub i's that you plug into your functions, okay? And so so there would be your formula for your if you were using the midpoint rule, which is basically you use the midpoint of each interval instead of the left or the right. You'll notice this. Let's go back to this one. You'll notice for this particular example, if we use the right end rule, we actually get areas that rectangles that are above, outside, or overlap the actual area that we want. So sometimes we call this an upper sum because it's bigger. That we know it's always going to be bigger than the actual area because those rectangles hang over the actual area, and that's going to happen in this case if we use the right end rule. On the other hand, if you use the left end rule, all of your rectangles will be tucked under the curve and not quite reach to the curve, and they won't cover it. So that'll be a lower end rule. So you'll see that referenced. All right. So finally, the idea is this: we we if we keep doing this, I guess I'll write it down here. We've run out a little bit of paper. Okay. The idea is this: if you keep doing this and let n get bigger and bigger, right, more and more rectangles, then you get better and better approximations. Or in other words, let n go to infinity, right? You want n to go to infinity. So here's what we have. Uh, the formula for the area is I equals 1 to n times f of x sub I, and I'm going to put a little star there because that depends on whether you're using the left or the right area. So it doesn't we don't want to have to keep bouncing back and forth. That little formula is going to change for x sub I. But anyway, you evaluate your function at either the left or the right end times the delta x's, and you add those up, and that gives you the nth area, right? The area of n rule in under n rectangles. But look, if you do this, if you take the limit of this, if you find the limit of this as n goes to infinity, now you actually have the actual area. You're not approximating it. So if we can find the limit of this this expression as n goes to infinity, then we will actually find the area. This is called a Riemann sum, and we'll explore this more in the next section. For now, you're not going to be evaluating the limit as n goes to infinity. You're simply going to be finding the area under n rectangles.